Now we have
Can I?
the former director, Professor Luciano Maiani, who will tell us about the 2000 announcement of CERN.
Well, thank you very much. I'm very happy to be here. And see. Non si sente?
No.
Che devo fare? Ah, no, wait a second.
No, no.
Probably. Mute.
Try.
Now it should go. Ah, no, sì. Pronto? Ok. Okay, so I'll try to tell you about the announcement of the year 2000. In a way, you heard distinguished people before, like Professor Schoppe and Specht and Stock, and they are the ones that prepared everything. And just arrived at CERN, just after the first year, I found myself that I had to make this announcement, which was not an easy thing because I was not so proficient in this business. So I tried to do my best, and I will tell you how we went there. So this was the This was the program of the meeting where the thing was announced. And let me tell you which was my view on that. And for me, the story started at the beginning of the 70s with a beautiful book of Steve Weinberg about cosmology, in which sometimes he says a very interesting thing, that to study the first minutes of primordial universe, you have to go to temperatures which go above the nuclear physics era, which is essentially the first 3 minutes where nuclei are formed. If you go back, then you have to know what happens to strong interacting particles, to the hadron matter at very high temperature. And at that time, there were 2 visions. The first was that there were only hadrons, and the hadrons were made by bootstrap or something, and that was worked out by Hagedorn, as Schopper has recalled, who noticed that if, as it happens in these models, the spectrum goes exponentially, you see from here that if you put here a Boltzmann factor, e to the minus m over t cannot be so large, because if t is very large, this is dominated by this one, and it will go to infinity. So that's a limiting temperature. You cannot go above a temperature. And this temperature, in fact, you can estimate by counting the number of resonances. And I have not the diagrams here, but you can do that. And you find that, of course, you have the resonance that you know, and if you go in large mass, you enter into a region in which there are the resonances that you don't know. But if you count, you stop there, you find a temperature of the order of 170, 180 MeV is reasonable, okay? Then there was another vision, which was that particles are made by photons, leptons, and quarks. And of course, if you have a gas of quarks and leptons, nothing happens. Temperature can be anything. Then, and so Weinberg concluded that at this time it was impossible to say something. But then came QCD and asymptotic freedom. And in this QCD, you can in fact put together these 2 pictures. And this was the great invention of Cabibbo and Parisi. how can it be? Well, it's very simple. You start heating a gas of hadrons. They heat up. When you go close to this limiting temperature, if you put more energy, simply you will produce more species of hadrons. And they will be essentially in contact. But if they are bags made by quarks and leptons, the bags will fuse, and you will go into a gas of quarks and leptons. So the idea was that the hagedorn temperature was just the critical temperature of a passage from a phase where you have a gas of hadrons and a phase where you have what we call the Quark-Gluon plasma. So roughly speaking, you have a situation like that. You put here, say, the temperature or the energy density of the temperature, and here you put the baryon number, the chemical potential, baryon number, okay? So, for instance, nuclei will be here. And there is a temperature here in which you go to another phase, which is made of quarks and gluons. You will see that things are not so simple, but anyway, there are questions. It is not solved the problem. For instance, is this a true phase transition? We think it's most likely a smooth crossover and things like that. But that is not important. This is the basic idea. You can put together these two very different pictures if there is this phase of Quark-Gluon plasma. And around the time, there were also starting lattice gauge calculation, and you see a very interesting thing happening. This is again energy, and you work at a certain temperature. And if you put energy into this system, at the beginning you have the hadron gas, and the energy increases, but you reach a limiting temperature. At some time, the energy density does not increase anymore if you divide by T to the fourth. That means that you have entered into a black body radiation, T to the fourth, okay? And that would be the Quark-Gluon plasma. So it all looked very, very reasonable. And I gave in my presentation this very nice picture. I like very much seeing the Jura from my office. So if you look at the Jura at the beginning of winter, you see it is like that. And if you are a skier, you are confined into one of these patches. You cannot move. Huh? But then more snow comes, and at this point, a skier can move here and there, even better here. That means that quarks are deconfined. That's exactly what happens there, okay? You start with the patches, which are the hadrons, but when the hadrons fuse, then you have another phase, and this is it. Of course, temperature goes in this way. Temperature increases when there is more snow. As Chopper told us, the heavy ion facility was done, this is the last one, was done by the collaboration of several funding agencies together with CERN. And, okay, this is it. And this now is a little better situation after several studies. This is another sketch of what is the phase diagram of quark of the hadron matter. This is what we saw before, and this is where SPS could be, Lhc, LHC. Notice that this you go to higher energy, and also you go to zero chemical potential, means zero baryon number. This is the condition of the early universe. So Lhc is closer to the early universe than was SPS, and LHC even closer. But then there are ideas about other phases. We would like to explore everything, and we still do not know that. I think that the next speaker will also speak about that, which is a superconducting phase with a condensed quark-quark system. This is a diagram that was done later by Beccatini and others, and roughly speaking tries to tell you where is the position where you are in this plane temperature and chemical potential at the various machines. And this is the SPS, and this is Rick, and there is not yet Alice here. Is not that. This was done around 2005, was prepared that. And this is what is called the little bang. It was very used at the time, this concept. You start from the collision, which produces a status which is here, let's say, suppose, so a state of Quark-Gluon plasma. This state expands and cools and goes through various stages until it reaches the Hagedorn temperature, the temperature at which the hadron coalesce and go away. This is what you see if you measure the distribution of the hadrons. You will feed them with the temperature. It will be the temperature of this, so to say, last scattering temperature. And there are signals that have to tell you if you are here, if you started from here, which are the J-psi suppression that Speck has said, the abundance of strange particles, because it costs less in the confined phase to produce an SS bar pair, and then also non-thermal photons, etc. These are the signals that you can try to see by looking here at the hadrons that have formed. And this is the Big Bang. It's very similar, the Big Bang. If you go back in time, we are here. If you go back in time, you are here at about 300,000 years after the Big Bang. It's when the atoms formed. The universe is transparent to light from here after, so we see this thing with Kobe or with something then. If you go back, you go to the nuclear era, where protons and neutrons coalesce to make helium and beryllium and lithium. And this is where you can go if you know only nuclear physics, atomic and nuclear physics. But you want to go further, and now we know how to go. We have a gas of quarks and gluons, and we can estimate that this condition, or if you want this condition, corresponds to about 10 to the minus seconds after the Big Bang. Now, of course, we would like to go further. This is where LHC has gone. And, of course, we would like to go even further, but that's another story. This is another seminar. OK, so this is it. Now, these are the slides that I projected at the time with the signals for the Quark-Gluon plasma, the strangeness enhancement, the J-psi and, in general, charmonium suppression, and was more doubtful the thermal electromagnetic radiation. And these were the data that already Speck has shown. This is the strangeness of, particularly here, the strangeness enhancement, here and here. I remember very many discussions I had with Querchik at the time. He was one of the people producing this data. And what happens? Use the space. Sorry, I'm pushing the wrong button. And this is the J-psi suppression, Na6, Na50, and this is the diagram that also Speck has shown with, this is essentially the ratio of of the normal production in normal hadron collisions as a function of the energy density, or if you want, as a function of the centrality of the collision, and you see that after a certain point there is a decline in that. And this is, again, at the time, a possible sketch of where we were in the phase diagram. As I said, here you have the nuclei, here you have the neutron stars, but this is AGS and this is SPS. And the idea was that the SPS could have started this little bang from here, and then cooling down, it would go to the thermal freeze out, which is where the hadron gas is, the hadrons that we see. And the conclusion at the time was that data provided evidence for color deconfinement in the early collision stage, and of course, higher energies are needed at RHIC and LHC to complete the picture and provide a full characterization of the Quark-Gluon plasma. This was at the time a picture of RHIC, which I'm sure you know, in Long Island, and RHIC was just entering into work, and this was a picture of the LHC. This was my slide, and as you see, the beginning of CERN of the LHC is 2005. Now, I wanted to give you a slide which concerned the story of the Lhc schedule, because that is an interesting story, and we live through it. Okay? What is the story? The story, for me, starts in 2002, when there was the recovery after the cost crisis, the definition of the cost of the LHC. Now, the schedule, the date 2005 had been determined essentially by the production of superconducting cables. But in 2002, it was clear, this is March 2002, it was clear that the cables were not going to be produced within 2005. And in fact, we estimate that the superconducting cable could be completed by mid-2005, which meant completing the dipole essentially a year after, 2006, and to have the first beam in 2007 and the first physics in mid-2007. So that was the redefinition that was done in 2002. What happened? Well, this went very well, because as you see from here, the superconducting cables were produced at the, well, not exactly mid-2005, but just a little bit later, just about the end of the year. Also, the dipoles went very well, because they had to be finished by July 1st, 2006. Well, the last one was in November 2006, so not bad. But at this point, something happened. The distribution line for the superfluid helium was given to CERN and turned out not to comply with the requirements. And it had to be redone, essentially. So this was the first delay, which, as you see, had nothing to do with the normal thing, and was about 1.5 years. And that explains why the first beam in 2007 arrived instead in September 2008. It's 1.5 years, roughly speaking. Now, unfortunately, as you know, at this point there was the accident due to the faulty interconnection between the magnets, and that took another 1.5 years to fix this problem. And this is Lynn Evans, that's the one that directed the construction of LHC until essentially here, until the first beams. And Steve Myers took over and he resolved the problem. And then we went to useful beam in 2010. So the 2010 is 3 years after the 2007, and that is the delay of the LHC. And it is like that, and that is the story. Okay, fine. I have to tell you that when the crisis came, there were many proposals from member states just to suppress ALICE and LHCb. And this is a slide of a research board in which the directorate announced that that was not acceptable. And so ALICE and LHCb survived. You are here, and you must be happy for that. And what about SPS? Well, SPS also survived, and there was the indium, the run with indium, which had a particular value, but it was not without pain because, sorry, because this running of the SPS was in contrast with a test beam for ALICE. And so it had to be reduced to 30 days. But we defended it, and we succeeded in continuing that. This is a wonderful picture of Lorenzo, which was presented in 2005. Now I am in the follow-up. I will finish shortly. And these are the famous indium data, which in fact sit down exactly on the lead data. So it's a confirmation of that, and essentially it confirmed that the effect was there. But now I want to close with a completely different subject, perhaps a new application for ALICE, which is not the Quark-Gluon plasma, but has to do with something which has arrived much later, the exotic hadrons which have been seen in E plus E minus and many other experiments. This is a very nice picture of the Charmonia. The yellow things are the Charmonia, which can be very well predicted. These are the JPC, the quantum number, which are very well predicted by the potential model. This is the J psi, this is the eta C, psi prime, etc., etc., etc. These are the established CC states. Not all have been seen. Those predicted and undiscovered yet are the gray thing, like this one or this one, etc. But meanwhile, new status have been added, which are what are called the XYZ mesons, neutral. The first one was the 3872, this one, 1++, but then there are others that have been added, the so-called Y states. And also, there are charged Charmonia, that is, states which decay into CC bar, but have a charge, like the so-called Z. This is the first one that was found. Then there are this one, and there are others. And the idea is that these are new kind of hadrons, a new spectroscopy. In fact, that's the title of this picture. And there are models. One is that they are loosely bound of molecules made of two mesons, like DD star. But it's a possibility that they have more compact structure. They are made of colored parts, bound by color forces, but not like molecules, which would be bound by pion exchange, and or even more fancy states in which you have a charmonium in the center and then a matter, normal matter around. And there is a very how to say, lively discussion about the proposals of these theta. But my point is that Alice could give a very good contribution to that. What you see here from Alice are the cross-section for light nuclei, deuteron, helium, helium-3, etc., as a function of p-perp. These are Alice data. As you see, the cross-section fall down very, very quickly. And the points here are instead in two different models of extrapolation, are the proton-proton data for the production of X3872, which have been renormalized to nuclear cross-section, to the PB lead-lead. Now, of course, in doing that, you have to use some models. But anyway, this already tells you something, that is that a particle like that is very different from nuclei. And it would be very interesting to see if also the other suspected exotic hadrons are produced in the quark-gluon plasma, and in which way are they produced like nuclei with a very steep falling cross-section, which is clear indication of a loosely bound state, or are they produced like the X that is with a cross-section which after all is not so different from charmonium, etc. And there is a long list of suspect particles that you should look and try to find in your data. The first one is the F0, then there is the X3872, which was seen by CMS but not yet by Alice, and the Zs, etc., etc. That would be an interesting subject to study. The last point is just this last slide, which I steal to Paolo Giubellino in a recent conference, that shows that in fact the work around the phase transition is not stopping. Of course, there is LHC, which is in this region, just well in the quark-gluon plasma region. Then there is Rhc. Then there is, again, a third, the other project, SHINE. Then there is a new laboratory in Darmstadt, which would be here, around that. There is Dubna, and there is Japan. So as you can see, the study of this transition is far from being completed. There are still many problems, and there will be many data to come. This is my last transparency. The February 2000 announcement was based on a circumstantial evidence, but solid. I think it was fully justified, and the subsequent investigation have showed that the situation was the one that we envisaged in this announcement. The SPS collision has produced a new phase of hadronic matter, and stay with us, the story is not finished. There may be other surprises. Thank you very much.